Thank you very much. As the voice in the sky said, I'm Hank Levy, Chair of Computer Science and Engineering. I'd like to welcome you to this second presentation in the 2015 Engineering Lecture Series, Robots to Web Trackers, Privacy in the Age of Smart Technology. This series is presented in partnership with the College of Engineering and the UW Alumni Association. If you're not a member of the Alumni Association, we invite you to visit online uwalum.com and learn more about the benefits of membership. Most of us have interacted with basic robots, like maybe you have a Roomba in your house that cleans your carpet or falls down your stairs. Robots are becoming more ubiquitous with expansion in the consumer market. Robots are going to change our life in the future. Simple robots we know today will soon be replaced by smarter, cheaper, and much more sophisticated machines. As you probably know, our grandchildren will probably never learn to drive. They will be driven by self-driving robotic cars. This evening, we're going to learn more about our robotic future. Professor Dieter Fox will explain how cutting-edge robots are learning to do 3D mapping, recognize and manipulate objects, and track human movement. Dieter is Professor of Computer Science and Engineering at UW, where he directs the Robotics and State Estimation Lab, and also leads the Intel Science and Technology Center for Pervasive Computing at UW. Dieter received his PhD in Germany at University of Bonn. He spent 2 years as a postdoc at Carnegie Mellon before joining us as a professor at UW in 2000. Yes. He's well known for his research in robotics and artificial intelligence, particularly for work on state estimation and perception applied to problems in robotics and activity recognition. In his spare time, I should mention that he is a monster of a bike rider, particularly when it comes to climbing mountains. Please welcome Dieter Fox.
Thank you very much for the kind introduction, and thanks everybody for coming. I can see the audience has some young robot enthusiasts. Welcome. Way to go. Today I'm going to talk to you about some recent and very exciting developments in robotics, and most of this work really happened over the last 5 to 6 years, and it's related to how we can get robots to perceive and understand the world around them in 3D. Before I'm going to give you examples from the work that's really going on in my research lab, I first would like to give you some context for applications where we already see robots in industry, for example. So let me start with the standard application that everybody knows, robots in manufacturing. This is actually a video taken in a BMW plant where they built their electronic cars. And these are kind of the standard robots that we have in mind and that have been built for decades already. And the main focus of these kind of systems is really that they do very, very precise motion. It's very repetitive. They can do the same thing thousands and thousands of times. They're highly calibrated. And they're, for example, not moving at all. It's mostly like not moving around on the ground. And they are pre-programmed to do these tasks. And also, it's very important that no human gets close to these robots because they're actually very dangerous. So there are special sensors in the environment that make sure as soon as something gets too close to the robot shuts down because they have no real sensors. They have no external sensors that tell them what is going on around them. Okay, so these robots don't really move around in the environment, but now if we look at a setting, for example, in an Amazon fulfillment warehouse, then this is what it looks like these days. Amazon just bought a couple years ago a company called Kiva for $750 million, and that was a big success for the robotics community. And if you ever wonder how Amazon makes sure that the right items get into the packages that get delivered to you, then this is how it happens. It used to be that actually people would run down these aisles and grab the individual items from the boxes, but now it's actually the shelves coming to the people. And these shelves are driven by robots, as you can see here, and this is a very large control problem. But in the end, you can see also that there are no people around the robots. So we have a similar setting where we have a very controlled environment. The robots are pre-programmed to do very specific tasks, but that is clearly one of the newer applications in these domains. Actually, before I came to UW, this is a project we started in 1998. We did this. If we can have.
My name is Minerva.
So this is a museum tour guide robot.
That operated in the Smithsonian National Museum of American History for 2 weeks in the summer of 1998.
The next exhibit is the blue washing machine at the very back over there.
And for us, the goal was really to have a robot to show people that we can actually move robots in populated environments. So the focus was on navigation, and the robot gave tours. And here you can see what happens if you don't only do your research in a lab, but if you actually get these robots out into the public. It was not a team member.
She can interact with people in real time using a combination of her voice and her facial expressions, both to clear her path and to direct people around her to the exhibits.
Could you please stay behind me?
He gets angry.
I need to get through.
And again, the main focus of this work was really showing that we can navigate with these robots safely among humans. But the key limitation was also that the robot, as you can see, it was just a moving box. So the robot couldn't manipulate anything in the environment. So it's very limited in the kind of things it could achieve. Very recently, DARPA, the defense funding agency, actually posted a challenge, which is a DARPA robotics challenge, where they said, motivated also by the Fukushima nuclear plant disaster, they challenged the research community and also industrial partners to build robots that could do tasks that you can imagine that might be important in such a disaster, where the robot, for example, could drive a car. As you can see here on the left, the robots had to be able to just walk up the stairs. They had to be able to pick up a drill and drill holes in a wall, for instance, or open a door and walk through the door. And in June, they had now the final run of this challenge. And let me just show you a brief video of what the winner did. This is a video I took. So here the robot is actually drilling a hole into this wall. So it first picked up the drill and now is moving around. You can see at some point the hole's open and everybody is very excited. So the people there cheering are from the team KAIST. This is from a South Korean team. On the right-hand side, you see the same robot now where the task was actually to pull this plug out of a power supply. This was actually not a normal plug, but it was just magnetic to make it a bit easier. And it's gonna do it soon. Yeah, there we go. So the main challenges here were really get these robots to walk actually without falling over. It turns out that this is still a very challenging problem, especially if the terrain isn't very even or there's rubble on the ground and things like that. But one thing you should have in mind is that these robots were actually mostly teleoperated, which means there was a person sitting somewhere else that could see the data that the robot recorded, and it could tell the robot, for instance, where the drill is, how to pick up the drill, and how to drill a hole into the wall. So if we want robots to do this autonomously, then we need these robots to be able actually just to look at the scene and figure out where the drill is and pick it up and things like that. And I'm going to tell you a bit more on the research threads that we're working on to enable this autonomous operation. Of course, today is a very big day. You might have heard about that. It's Back to the Future Day. This is kind of transportation envisioned in 1980.
Roads? Where we're going, we don't need roads.
That was about flying cars. So we haven't really reached that level of excitement when we think about transportation, but I think some recent really exciting developments are in the self-driving car domain. So here you can see on the upper right one of the Google cars that they use especially for their testing. And down here you can see kind of what the world looks like to that Google car.
Spot the orange signs and cones early to alert the car of the lane blockage ahead, and we can change lanes safely. You'll also notice the vehicle typically moves to keep a safe distance away from large obstacles, like this truck stopped on the side of the road.
So these purple boxes are other cars that it's tracking, so it needs to know where the other cars are.
Notice the red fence and railroad sign that appears to the computer as we approach the intersection.
It can recognize street signs.
Wait until the tracks are clear of other vehicles before proceeding.
And also people in the yellow boxes.
Cyclist as a special category of moving object. Watch in this example, when the cyclist holds up his arm, our software detects the hand signal and predicts his movement into our lane. The car knows to continue yielding to the cyclist passing by, even when he changes his mind, multiple times.
So they're certainly more patient than most of the drivers we know, or I know.
Now handle smoothly and naturally. See you on the road.
Actually, now you might ask, how does the car really do this? And the main sensor that really enables this development, especially for the Google car is focusing on this, is if you look at the picture of the car on the upper right, then you can see that on the roof there's this little sensor, and that is the main sensor that Google is actually using to drive these cars. There are other companies that are looking at doing this with cameras and radar. For example, Tesla just enabled people to download a new control program that lets you drive, that lets the car take over control on the highway. And I haven't done it. I don't have a Tesla yet, but I heard it's working actually surprisingly well. So now let's look at the data that the sensor actually gives you. And this is kind of a 3D laser scanner. It costs $50,000. I'm sure Google is working on a cheaper version. But you can see this is the data that the car or the computer is observing. And you can see this already gives you the sense of the world in 3D. And from that sensor data, what we have to do is then extract kind of information about where the other cars are, how they move, where people are, street signs. And for those, of course, we also connect camera information. The kind of robots that I really want to talk more about today are these kind of robots that you might call the helpers in the home, or some of you might have heard of Rosie the robot. It's funny, me growing up in Germany, I hadn't heard about that robot before, but I hear it's doing things like that. So imagine if you want to have robots that really do help you in your household, for instance, right? They can make your breakfast pancakes, they can fold towels. Some of you might have heard about this kind of research. So these are all research robots that are being deployed right now, or also helping people with physical disabilities. So here's a robot actually helping, kind of just pulling up the blanket for that person, or holding a shaver so the person can shave. And on the right-hand side, of course, you can a robot kind of sweeping the floor. But for this, nowadays, we, of course, use more like the Roomba-style robots. But if you go from this previous robot that you've seen to these kind of systems, then you can also recognize that it's suddenly crucially important that these robots actually interact with the world. For the Google car, most of the interaction is about not interacting with other cars, right? You don't want to crash into them. But for these robots, suddenly, we need them to touch things, to pick things up and move things around, or in the towel folding, actually move them in a certain way. If we now go back about 6 years ago, these were the main sensors that we used in the research community. On the right, far right, you see the Velodyne sensor. This is the same sensor that I showed you on the Google car. If you wanted to track, for example, the position of people, what you had to do is you had to put the person into such a tracking suit, put little white markers on them, and then have a lab equipped with tracking systems that can track the position of the person. On the lower right, you can see, of course, camera is a really nice, cheap alternative. But the problem is that a camera doesn't really give you the kind of information that we as roboticists really care about. For a robot or for a computer, the camera image is just a 2D array of colors, but it doesn't readily tell you where the objects are or how far things are away in the world. That is why, actually, in the robotics community, for mobile robots, the main sensor that we really focused on is a 2D laser scanner, a SIG 2D laser scanner, that you can see. It's like the blue coffee machine on that little robot there. So what that robot tells you is kind of like the Velodyne, but just as a 2D laser sweep. So what it does is it gives you information about obstacles in one plane in front of the robot. And what you can do with this, you can build a map like that. So this is a 2D map that we built actually in the Allen Center, where white space is free space, and the black things are the obstacles, and the blue is the path the robot followed when it did the mapping. And I'll show you briefly how actually we can build such a map with a laser scanner. Here you can see the robot moving around, and what it does is it takes consecutive laser scans and stitches them together, kind of how you feel like nowadays many of these photo stitching systems are working. Okay. Now the problem is that the stitching process involves a tiny bit of error all the time. So as the robot gets back to where it started, you will see there's some offset. So in our system, we develop techniques that can detect that the robot got back to where it was, and then we can realign the map to be consistent. You can see another realignment process going on now. You can see that the whole map is slightly shifting, and that is after the robot detects one of these what we call a loop closure, which enables it to recorrect things so that everything looks consistent. And these maps are great for navigation. This is the kind of map we used, for example, in our museum tour guide robot project. But you can also imagine if you want to have a robot interacting with objects, picking up objects, that sensor is not going to do this for you. So we need a much richer sensor than that, and again, something that goes closer to maybe camera data. And that is when, in 2009, at the time, I was actually director of the Intel Research Lab here in Seattle. And through that, we got our hands on a prototype for the Microsoft Kinect gaming sensor. And I just want to show you briefly what this sensor is about, or what the system is about. So
you can't recreate a finale like you've seen it.
you might have seen this, but this is for the, the early prototype was actually called the Natal system, but the Kinect system. And Robotics just got very excited about this, not because we are so enthusiast skateboarders or try to jump around in front of video games, but actually what got us excited is the sensor that enables the Kinect system. Okay, so what I want to show you on the next slide is an example of the data stream that we're getting with one of these cameras. Okay, what you see on the left is just the standard kind of color video data. And on the right, what we show is information about how far things are away in the world. So the color coding there says red things are close, then we go to yellow, green, and blue things are far away. So what the Kinect sensor actually gives us is, for every pixel in the camera image, not only the color of that pixel, but also how far it is away in the world. And that is crucial for robots, because robots need that kind of information if they want to avoid crashing into things or if they want to pick something up. It's really important to know how far it is away, and that is what this sensor gives you, this kind of information. And what's, of course, also very exciting, at a price point of about $200. Okay? So in the rest of this talk, I want to give you some examples of how we can use these sensors to enable robots and to enable computers in general to reason in 3D, to use this depth information to get much richer models of the environment. And I organize this kind of into different parts, where the first part is where we try to see how can we model environments like a building, or how can we model 3D models of people. Then I'll talk about how can we actually model individual objects, because it's not enough to have a model of a house. You also want to know where the objects are in the house. Then I'll tell a little bit about recognizing these objects so that you can know where the coffee markets and things like that. And then I'll conclude with some final thoughts. So what I'm going to talk about now is all kind of work that's been going on in my lab over the last 5-6 years. So first is mapping. So as a roboticist, we care a lot about kind of building these maps of environments. And now the question is, with this kind of sensors, how can we build a 3D map of an environment? And the task you can break down into different sub-steps, and all the mapping algorithms kind of share that, let's say, global structure, where the idea is we need to take all the data that we collect with a Kinect camera as we're walking through the environment, and we need to stitch that together to come up with a map, just like you saw with the laser map early on. So the first step is actually we need to take 2 consecutive frames, camera images, or depth images in time, and we need to see how we can align them so that they match into each other. So we do the stitching process, and if we can align them well, that tells us actually how the camera moved between these 2 time steps. So that gives us kind of a forward estimate of how the environment looks like. And then we need a way to detect these, what we call loop closures, which means we need to detect that, ooh, I'm coming back to a location where I started, for example. And how we do this is we just compare images we see now with a collection of images that we've seen in the past, and if we get a really good match, that tells us that we got back to a location that we already visited. And once we have such a detection, we need to use that information to globally adjust the position of all the camera poses. In this talk, I'll only show you all of this kind of, mostly with videos and animations, but you should have in mind that actually what's going on there is some really statistical estimation that we're performing here, right? I'm not gonna go with you through the painful process of actually going through this equation, but I just want to give you a sense that actually these things on the computer, we have to phrase them in a way of an optimization problem. So the first step is, for example, this frame-to-frame alignment, where we're trying to optimize over the motion of the camera. And that motion is a transformation that we try to find such that the 2 data sets match as well as possible. And then finally also, when we get the global alignment, we're trying to optimize over all the poses of all the camera views we've seen and all the features in the world. So these are actually pretty substantial optimization problems, but for many of those nowadays, actually you can download packages that do that for you. So I'm not going to give you more details of that, but have in mind that this is actually what's going on underneath all these pretty videos. So here's an example of now with the Kinect mapping a hallway. And you can see that we have, again, this slight misalignment problem. but we can detect that automatically by comparing images, and we can then fix that and realign the map and get a globally consistent map of that hallway. Okay, this is just an example of how we can build a 3D map, for example, of this environment. Now, the next thing we did is actually a friend of mine is a faculty at MIT, Nick Roy, and he is working a lot with quad rotors. So we decided, let's put a Kinect on a quadcopter. And here you can see kind of the trajectory of the quad rotor flying around. And now, with our mapping technique, we can build reasonably good 3D maps of the environment. And you can imagine that these kind of maps you can use for navigation, right, for a robot, so that it knows how to navigate without crashing into obstacles. You can do path planning in these maps. How do I get to a different room in the environment? But this is also a nice example for something, for example, that you could use very well kind of in a disaster area. For example, if you have, after an earthquake, there's a building and you don't want to send people in, you could now imagine you can set such a quad rotor into that environment, and it's going to build you a nice 3D reconstruction so that you can see what is really going on in the environment. Okay. Just as one other example, let me show you a 3D map that we're building of a colleague in electrical engineering, Klavins, is doing work in synthetic biology. So this is a map we built of part of his lab, and you can see that it's actually pretty accurate these days, right? We get pretty good representations of these surfaces and the colors, but you can also see some of the limitations. So for example, on the upper left, these kind of transparent objects are not really well visible to the depth camera, so you can see that the map up there is not really accurate yet. Okay? But you can also see that we now get representations that are in 3D, and the robot can perform reasoning about that, and you can even imagine if it could detect that down there these are drawers or cabinet doors, it could perform planning and open them autonomously. And now I want to go to one other example where the problem is if we want to model something that's actually moving while we're mapping it. So far, all the environment was static, which means as we are mapping, the only thing that's moving is the robot or the camera. Nothing else is moving. So if you want to apply these techniques to a moving object, which is, for instance, a person, then you can see what's going to happen here, actually. So this is Richard Newcomb moving his head around, and if we just use these techniques that assume that everything is static, we get a model that is clearly not very accurate, especially he has a much prettier nose. Okay? This is now pointing to work that Richard Newcomb, who was a postdoc with Steve Seitz and me, did here at the University of Washington. And this is a work, it's called DynamicFusion. And the idea of this work is now we take as input a moving stream of depth video. We now estimate in that system how that person or how that object is moving. And then we can use that estimation to update a 3D model of the person where that model is not moving, but we're separating the motion estimation, and we can then get a non-rigid reconstruction of that person. And this is Tanner, grad student in my lab. He's working a lot with Richard. So Richard wasn't able to join us here today, but we'll try to see if we could do a quick live demo of how this works. And robotics live demos are always very, very scary. So I expect this not to work, but we'll give it a try anyway. And for this, we need a volunteer. And actually, I just see someone coming up here on stage. This is my daughter, Carla. And she volunteered happily to show us how this now works. So this is just, again, this is a camera you can buy for $200. There's nothing special about it. I'm just trying. So you can see here that the system, what it has to do is, while during that reconstruction process, it has to estimate how she's moving, how Carla is moving, deforming, how we call it. And at the same time, we need to estimate how the camera is moving because the camera is also not static. And we have to do all of this in real time and jointly. So this is a really big optimization problem. Now you might ask yourself, like, what could that be useful for? Of course, things like for clothing, you can fit the clothing or you can measure the size of people and things like that. But for example, a colleague of mine, Kat Steele, she is a professor in mechanical engineering, and she's working with a medical school to investigate movement disorders. For example, after a stroke or people with cerebral palsy. And one of the problems is that in order to investigate these problems, you need motion data from real people, how they move. And right now, this requires huge motion capture labs. But with this kind of technologies, you could even collect the kind of data at home, right? And there's, for example, research going on in how could we detect, for example, cerebral palsy early on, even in the way a baby moves. And in order to do these kind of studies, you need a lot of data in order to investigate this. And this is the kind of that you can see with which we can do that. Here on the right, what you can see is kind of how she's moving, and these little arcs are showing also at the same time kind of the motion vectors of this, which means that the system can really analyze how she's moving around. Okay, so this is just a visualization. And of course, for robot, it is also very useful because now a robot can observe a person, can see how the person moves, can also identify, for example, where are the fingers, how are the fingers moving, and things like that. So this is extremely useful for robots as well. Okay, so yeah? All right, awesome. Thank you very much. Thanks. All right, so now what we have so far is we can build models of environments, of things around the robot, but we haven't talked about objects at all yet, right? So this is just models that are kind of 3D shape models, but they don't reason about what is in the environment. So the next thing we wanted to look at is, can we get a robot to kind of discover objects in the environment as it's moving around? And there are two approaches that we looked at. One is what we call a passive approach, and the other one is more active approach. So the first thing you can do is, you can imagine a robot goes and kind of builds a model of part of a kitchen, and the next day it gets back and it looks at the same area, and just by looking at what changes in the environment, it turns out you could imagine that you could actually detect where objects are. Okay? And now it comes back and it again compares these things, and now it can detect other objects. So you could imagine now a robot in the home, because robots won't know all the objects, for example, in the house, it could over time learn about more and more objects in your home and reason about their shape and, for example, how to pick them up. So how do you do this in a little bit more detail? Here's a scene, for example, of a table. So this is already a 3D map that we built of these tables. The table. So the table has obviously different objects on them at the different points in time. The first thing we need to do is we need to align these tables. So we need to know which parts of the scene of the table map to which parts. And this is here just showing kind of an overlay of the aligned tables. Once we can do this, we can actually pretty easily do change detection on these surfaces. So what we can do is we can look at any surface, for example, on the left scene, here, for example, seen by this red circle. Because we have these scenes in 3D, we have them aligned, we can check out which surface this would be in the other scene. And because we observed that scenes from many different camera viewpoints, we can actually also check out what that point looked like in the video frames that looked at that scene. Okay? So now what we can do is we can compare what that surface looked like in this scene, for example, green, and we can compare it in the different frames what it looked like in the other scene. And then we can detect when there are changes. And we do this, in this case, you can see here we're just computing what we call probabilities for motion of a surface element. Okay, so these are all probabilistic estimates because the data actually turns out to be pretty noisy. And once we do this, we can actually now visualize what this probabilistic estimate looks like. And here you can see for these two scenes an estimate for what changed. So in the left scene, black means, okay, nothing changed between the two views. In white, these are areas where with high probability something changed. And gray is where the system doesn't really know well. For example, because the color is very similar or because the robot didn't see it due to occlusion. Now, this is still pretty noisy, but we can feed this into some additional probabilistic reasoning techniques and do some segmentation on that, and then we're getting actually a very nice clean segmentation of the objects that changed in these scenes. And once we have that, we can more or less cut them out, and we now get a collection of the scene, background, and the different objects that were there. And you can now imagine if a robot keeps on doing this, over time it can learn about more and more objects. The limitation of this work is really the robot is still very passive. It's just looking at the scene. If I would ask you, okay, you should memorize this object here, I think what we would naturally do, we wouldn't really just walk around here. We would just pick it up and look at it. Okay, so in the next line of work, what we really wanted to see is if we can enable a robot to actually actively look at these objects. Here's just one more example of another scene. So here's a chair that was toppled over, and we can also very nicely detect that chair through this scene change detection. So now the robot has a model of the chair as an object in the environment. So here's an example of what we call active object modeling. So here's a robot manipulator. You can see the video stream on the upper left. And it's moving, actually a beer can, through its hand. And on the right-hand side is how it can use that data to do a reconstruction of that object. Okay? So it's rotating it, and it's getting now a complete kind of turn around the object. This is very similar to building a model of an environment, right? Now we're just building a model of an object. And now, let's say you rotate it, and now it can see the upper part of the can, and you can see that it closed that as well. Now, the problem is, if you do this, you cannot pre-program exactly how the robot should move in order to build a perfect model, because how you move, the model depends on the shape of the object itself. So we cannot pre-program them. We need to enable our robots to do this automatically. Here in this work, what we did is we used the notion of uncertainty. So this is a surface model of an object as we are modeling it, and red means the robot has high uncertainty in actually the surface of the object there, and silver means it's becoming more certain because it's looking at the surface multiple times. If it just looks once or it doesn't really see it, then it has a high uncertainty. And can anybody see where these holes might come from? Yeah?
Maybe like the robot holding onto it?
Exactly. That's where the robot has it in the hand. Great point. So now we can use this notion of uncertainty, and for those of you who are interested, we just measure this by entropy over the distribution on the surface. The robot can actually automatically decide on how it should look at the object in order to reduce the uncertainty. So here's a real robot. Initially, we just move it around the object in a predetermined trajectory just to get some initial idea of what the model looks like. And then after a while, it has some reasonably good model already. And you can see this here. Now, red means in this part of the model, it's still very uncertain because it was mostly occluded also. And we now determine how should the robot move the object so that it can get a better look at those surfaces. And you can see now that this area down there, because it can really look at it more closely, we have lower uncertainty, which is the silver area. And it's kind of holding the stuff to the camera, which is on the upper left there. And I don't have that in the video, but what we actually also did is at some point the robot can determine that it cannot further reduce the uncertainty because it's holding the object in the hand. So what the robot actually does is it puts it down and then determines how to pick it up again so that it can also model the occluded areas. Okay, so this now enables a robot to go into an environment and actively just learn about these objects that are there and build 3D models that it can then later use, for example, to pick them up in a more efficient way. So now I would like to talk about another part related to objects, and that is about how can we actually now recognize certain objects, or how can we track as they are moving through the environment. Where we are so far, when you think about we can build models of environments, we can build models of people, we can build 3D models of objects, but this is clearly not enough because you want to be able to tell a robot, okay, bring me my coffee mug, or put the cereal box in the cabinet, or put the cereal bowls into the dishwasher. So if you want a robot to actually be able to execute that, the robot needs to be able to go in the environment and know what the cereal boxes are, or what the cereal bowls and coffee mugs are. So that is about recognizing objects as belonging to a certain class of object. So what we want to do here is imagine you have this 3D scene, and we can build these as you've seen so far in the previous animations. So what we would like to achieve is not just have a scene that looks nicely colored. For us humans, this actually is easy. If I would tell you where's the cereal bowl, or where is their baseball cap or sofa, you look at it and you immediately see this. For computers, it's actually not that easy, because the input is still just a 3D model, or is still just a bunch of colored pixels. Okay? So where we would like to get is from this representation to a representation that's more like this, where now we colored the different points in the cloud by the kind of object they would belong to. So the red ones here are the sofas. We can detect a coffee table, a baseball cap, and things like that. Let me just briefly show you how we can actually do this on a robot. The first part to this is what we call image-based object detection, and this is also a highly active area in computer vision, where the idea is you have an image, and you would like to detect, for instance, let's say, cereal boxes. Where is the cereal box in the image? So what you do is you extract many, many examples, many, many images that you label with, this is where a cereal box is. So you tell the computer where cereal boxes are in the images. We can use this with machine learning techniques now to learn classifiers that will tell us that looks like a cereal box and that doesn't look like a cereal box. We can train this for these little green windows. Okay, so this is the size at which an object detector reasons. And if we now want to see, is there a cereal box in that image, we can slide that detector over the whole image. And for each pixel, we just ask, does that look like a cereal box, yes or no? And then what we get out of this is something like that on the right side, where bright areas would be, for example, there's a cereal box, looks like a cereal box, and the dark areas are where the detector doesn't respond. Okay, so we can do this very well based on individual images, but the nice thing is that in our setting, in the robotics context, where we have not only an image, but we have actually a 3D map of the environment. Okay, so now let me tell you how we could take advantage of the fact that we have a 3D model of the environment. So first of all, we have different images that the robot has looked at. Yeah, these are the images that the robot can use, as you've seen previously, to build a 3D map of the environment. So this is now a zoomed-in part of a 3D map that represents this area that the robot mapped. And in green, you can see a little cube there. Okay? And what we would like to know is, what kind of object does that little cube belong to? It's in 3D. Okay? So in this case, you would say it's a coffee mug or a handle of a coffee mug. So if you want to do this, what we can do is we can first see what that cube looked like in the individual images. We can project that 3D cube back into the individual images that we recorded. Okay? So now we have these little boxes in the images. And for each image now, we can ask, okay, how much does it look like a cube? Just using the techniques I showed you on the previous slide. And we can use these detector responses and feed them back into the 3D model. So now every voxel in that 3D map represents kind of how much it looked like a coffee mug, for example. Okay? And once we have that, we can then reason about the different objects in the environment, and we can do some spatial smoothing, and then we get something like this, where I'm going to show you kind of as the robot builds a map of that scene, and the coloring indicates what the robot thinks what kind of object it is. So it first detects a coffee table correctly, it detects the sofa down there, and it does that again by integrating all the information it's seeing into that 3D map. Okay, so now we have a robot that can not only reason about 3D shapes and things like that, but you could tell it, okay, bring me my baseball cap, because it can detect what a baseball cap looks like. Okay, even though, and part of the research is here also, it should be able to do this for a cap or a coffee mug that it has not seen before. This is what we call generalization in machine learning. Here's another example of two scenes where you can see kind of that we can very nicely kind of cut out these objects and detect the type of objects we are talking about. Now that we can talk about objects and their 3D shape, the next question is, how can we do manipulation of them? Okay, so here's a project that actually Tanner did when he visited the German Aerospace Society, which is south of Munich, DLR, and they have a really cool robot, as you can see here. And the task for that robot is we would like it to be able to pick up, let's say, pretty small objects and manipulate them with these arms. And also you can see here's a Kinect camera. And the approach is, the notion of this work is very similar to, I think, what is going on when we want to pick up an object, where the idea is if I want to pick up this bottle here, I'm not just going to kind of look at it, close my eyes, and then try to grab it. I'm actually looking at the object, and I'm looking at my hand at the same time so that I can guide it to the object. Okay? So what we need to do is to do something like that on the robot. The robot needs to use the camera data to detect where its own hand is, okay, because there's some uncertainty in that position, and to detect the object. So that led to some research direction where we wanted to track what we call articulated objects. And articulated objects are objects that are not rigid, let's say like a coffee mug, but these are objects that can move. Examples are people, the whole body, a hand, or here you can see one of the robots we have in the lab. This is a Baxter robot. Okay? And the articulation means that underneath that 3D shape, there's some kind of skeleton that constrains how it can move. So here on a human, for example, the shape model says, here we have a certain rigid shape, and it's connected to this rigid shape through a joint that can move in a certain way. And we can do this for all the joints in the human body. Okay, so this would be a shape model of a person, and we can do the same thing for the hand. It turns out that if you want to track a hand of a person, it's a 27-dimensional search problem. So how do we now track such an articulated object? Here's just a visualization of kind of a simulated data, where you can see this is a robot hand, okay, and you can see it's grabbing an object. Now what you can see as these little black dots, this is kind of one of these depth scans. You can imagine, so these little black dots indicate what the robot sees, okay, and you can see that somehow the observed data doesn't match the position of the hand and of the object. You can see it's kind of slightly rotated against the data. So what we need to do is we need to bring these two things together so that they match. And how we can do this, just move on to the next slide. Here we go. We can very quickly estimate for each point that we observe, each of these black points, we can estimate how far it is away from the object model that we're tracking. And we can use this again in some optimization technique to optimize the match between this, which means we want to minimize the distance of the observed point to the observed model. We can also do things like, if we know that that robot hand, for example, is touching with these two fingers, we can take that into account when we do our optimization and force the finger to be in touch with the object. Okay? We can now use this kind of reasoning and tracking capability on this, oh, sorry, I went one too far here, on this robot, and I'll just give you a brief example of it picking up this object. You can see on the upper left the view from our camera. Upper right, you can see just an external view. In the lower left, you can see our system tracking the pose of the robot hand and the object. So the robot now can really use its hands to pick up the object. We can track it in real time. And it can also now, interestingly, for example, in this case, it will drop the object. And because the tracking system is working so efficiently, it can track the objects as it's falling down. So the robot could now reason about saying that, okay, that didn't work out, so let me pick up the object again. Okay, so similar, I think, to the kind of reasoning that you would see in a person. Let me give you one quick example here, also related to manipulation, where the idea is if you would like a robot to move objects in a certain way. So for instance, here you could imagine that you would like the robot, if it's holding a cup that is full of water, to move the cup such that it stays upright. And at the same time, if you look at the table, you would not like the robot to move the cup above, for example, the laptop and the remote control, because that's a bit too risky. Okay, so you would like the robot to move around these objects while holding the cup upright. Now the question is, how can you program the robot to do this? You could, of course, hire a programmer that sits down and writes a program to do it, but we rather looked at some work, and this is work by Matthew and Arun, on machine learning techniques where you can tell the robot how to do this actually by just giving it examples of what you mean. So here's a demonstration, student showing the robot, for example, how to move that cup. You can see she holds it always nicely upright. And she also moves it in a way that is not, if you look here at the top view, not above the laptop, for instance. And now what we can do is we can use these demonstrations to teach the robot how it should plan when it's moving its arm. Okay, and here you can see now an execution of the robot performing a navigation task while avoiding, for example, getting on top of the laptop while trying to hold the cup as upright as possible. Okay, and this does not work for that configuration of objects, but the robot really learns that it should try to hold the cup upright and should try to not move it above a laptop. So, which means if the laptop moves somewhere else, it will be able to detect it and avoid that as well. Okay, so this is kind of machine learning techniques that makes it much easier to program these robots to do things the way we would like them to do. Tanner's tracking work doesn't only work for robots, but we can also use it to track, for example, a person's hand. So what you will see here is tracking of a hand, so you can see the 3D model of the hand along with the points. This is the data that we're using from the camera. And this is the speed. The hand did not quite move that fast, but this is the speed at which we can actually process the data. Okay, you can see that this is actually very efficient. We can now, because it's a very general technique that doesn't make assumptions about the objects, if you give it an object model of a person, we can now track a person as well. Here you could see there was actually a small tracking failure. I'm not going to show you that again. And there are some caveats here that we could talk about in detail, but you can see that now we have robots that can really perceive people and can see how they move and learn from demonstrations from the people. So here's another example of work we're doing, again, in Eric Klavins' Wetlab, where now we can also track a person. And a larger project here is actually trying to track activities in a Wetlab. What you can see here on the right, these are 3 depth cameras that we put in the lab. And the person is performing certain protocols that they do in the wet lab. And the idea is that we would like to use these cameras to very accurately track what the person is doing and how the person is doing this. And this is a collaboration with Intel and part of our Intel Science and Technology Center that we have here. So why might Intel be interested in that? Well, the idea is actually, the general notion is we want to be able to track these kind of activities at a very high accuracy. And for example, one big problem in science research in wet labs these days, it's the notion of what we call reproducibility. Which means, for example, when I talk to Eric Klavins, how they do many of these experiments, it turns out it's, for example, a postdoc doing a certain experiment, like pipetting with the test tubes. They get a certain result. And then he tells them, OK, now go back and try to do the same thing again. They do the same thing. They get different results, and they have no idea why. And they don't even know exactly how they did it the previous day. So nowadays, how you do these wet lab protocols is the students actually most of the time just write down in the lab notebook what they were doing. And then you publish this in your papers, for instance. But with such a system, you could now go and automatically not only record what the people were doing, but also automatically analyze how they were moving, because it actually matters how you shake a test tube. Okay? So we can now automatically do these kind of things, and this is important not only for reproducibility in science, but also, for example, you think about manufacturing, or Intel cares a lot about maintenance of these very fancy, very expensive machines, and you would like to be able to see if someone, for example, makes a mistake while doing this. For us also, of course, interesting, you could maybe do this in a kitchen cooking, the system telling you how to cook a certain recipe and giving you guidance and what you might be doing better when you're cutting the onions or things like that. And of course, if you have this data, you can use it to teach robots how to do these things just by observing humans doing it. And with that, I'd like to come to my conclusions. So the first part is really, I think, The very exciting new developments that started, I think, really also with these new depth cameras is that now we have robots that see in 3D. And these advances were due to, on the one hand side, new sensing technologies, but also very much on the algorithmic side, new ideas on how to process that data, new actually hardware. So a lot of that work uses graphical processing units, GPUs, which are these graphics cards that the kids buy to do computer gaming. Okay, so we actually have in our lab, I think, some of the best graphics cards. So we could do the fanciest computer games that you can imagine, but we're mostly using them to process actually this kind of data. But also, again, a lot of progress on the algorithmic side on how we can actually use that data and extract 3D information from that. And we really enable these dramatic advances on how robots can interact with the world and how they can learn about the world. I think the next generation of really these personal robots is really going to go, we're going to have robots that can learn, detect, and manipulate objects in an environment. So they can learn about these new objects. They can interact and collaborate with people. I haven't talked about that a lot, but you can imagine the kind of information that we're extracting from these sensors helps robot to really interact with people and see, for example, when a robot collaborates with a person, when the person is ready for the next step, or what the person wants from the robot. And we're also seeing more and more of work going on in having robots that can automatically learn new skills and do things better than they did initially, which means constantly adapting and just getting better. Application scenarios I think we're looking at, of course, is self-driving cars is obviously at some point going to happen. We might see more gradual process where the cars are becoming more and more autonomous, let's say. In the healthcare and elder care section, so for example, in the home environments, having robots that help, for instance, people with physical disabilities or elderly people to stay at home and where the robot just helps them at certain tasks for which they might be useful. That is also, I think, one of the main domains where robots will first be useful in the home because for the kind of chores like washing your dishes or so, they're just still too expensive. So many of these prototypes we're seeing here cost like $100,000, $200,000, and clearly that's not a good cost benefit for people just to get your dishes washed. But there's a lot of work really reducing the price of these robots and also getting them more and more capable. Small-scale manufacturing, which means getting robots into manufacturing sites where things change very quickly, where you cannot use these kind of automation robots that I showed you in the very first video. And disaster response, I showed you some examples of that. I think this is, a very nice area where they will have a big impact. Privacy and security. If you look at all these robots, if you want to have a robot that's really useful and can interact with people, these robots must be able to really see and listen what's going on around them. And that, of course, raises then many issues with respect to privacy and also security. Right? So a colleague of mine, Maya Chakmak, who is working on human-robot interaction, did a study where they said, okay, if you have a robot that helps you certain tasks in your home, and let's assume you can, or someone could teleoperate the robot so that the robot can actually pick up objects it doesn't know, then suddenly this raises issues like if you have a credit card lying around. Now suddenly someone who teleoperates your robot could maybe read the credit card or social security number information, things like that. So we need to make sure that we take care of these kind of problems. And some of the challenges are really how do we get robots not to physically harm people or destroy objects around them to do crazy things. And that is very much also, I guess, let's call it an engineering problem. Right? But then also, how do we make sure that they don't perceive or store and also especially share personal information about your house? Because suddenly, again, you have a moving computer that has a camera and maybe a microphone. And also, finally, of course, how that they can't be hacked. There's some research on showing that certain types of these robots that you can buy, they can be hacked, and then someone might actually get off the data. So there's a lot of work to be done in that area as well. And with that, I'd like to finish with acknowledgments. And of course, all the work that I presented to you was really done mostly by graduate students in my lab in the UW CSE department. So here are the ones that were really active over the last years. Also, we're doing a lot of research with undergraduates. So they also get many research opportunities in the lab. Of course, several postdocs, faculty collaborators from different departments, not only computer science, but also electrical engineering. We work with people, mechanical engineering, aero, astro, and funding comes mostly from the National Science Foundation, Office of Naval Research, Army Research Lab, DARPA, and Intel through the Science and Technology Center for Pervasive Computing. And with that, I'd like to thank you.